Okay, we're going to talk about iron. So iron, everybody thinks of it first of all as being a good thing. They think of, well, you need iron to make your hemoglobin for your blood, otherwise you're going to be anemic. And I can remember when I was young, I used to like to eat Raisin Bran cereal because it had more iron in it. But I can tell you now, I would avoid anything with iron added to it. And men especially have a problem with iron overload because men don't menstruate. Men start accumulating iron by the time they're 20 years old. Iron, again, can be good, of course, when it's bound to our hemoglobin. It's an important part of enzymes like the cytochrome enzymes. It's also part of ETC, electron transport chain, the iron-sulfur clusters for transferring electrons down the intermitochondrial membrane. The carrier in the blood for iron is transferrin. It's like a wheelbarrow that holds two iron atoms in the blood. Binds very tightly to iron. That's an important thing in the body, is to bind tightly to iron to keep it away from bacteria, because bacteria want to grow with it. Okay, ferritin is the name of the protein that stores iron within a cell, and it stores a lot. 4,500 molecules of iron is stored in a cell per ferritin molecule, okay? So iron, why is it so special? Because iron is a transitional metal. Iron, being a transitional metal, has a variable valence, meaning that it can be Fe2 plus or Fe3 plus. It actually even has more potential valences, but those are the main two worth knowing about. I remember ferrous sounds like deuce for two. Ferric, the E sound reminds me E and 3, the long E sound. So those are the two main forms that are important for us. We store it in our body in case we bleed. You know, our ancestors had to worry about, so-called being chased by a tiger in the dark as the classic response to danger and stress. And basically, if they bled, they wanted to be able to reproduce their hemoglobin bound to iron very quickly. And so that's why we keep a lot of storage iron. We lose a little bit of iron in our sweat, but it's really pretty minimal. And I think the reason this all happens this way is humans did not evolve eating meat, okay? And meat has hemoglobin-bound iron. And the hemoglobin-bound iron is highly absorbed, in the ballpark 40–50%. In comparison with typical plant iron, usually absorbed only about 5 or 10%. So the body's good at regulating the amount of absorption of iron from plant food sources, but it is not good at regulating the amount from meat. I think it's because hemoglobin, the heme molecule itself, is so energetically expensive to synthesize that the body has a carrier system to take it up, because we take up too much of it whenever we eat a meat product. Okay, now how does free iron get into the blood? So by the way, this is a totally different thing here. Free iron is bad. Usually it'll be referred to as unliganded. To ligate something is to bind to it. So unbound iron, free iron out by itself, not connected to any carrier protein, is dangerous. And here's the reason why. The iron can undergo what is called redox cycling. That's an important word there. In terms of understanding iron, that's a key thing. Redox cycling. So it can cycle back and forth from Fe2 plus to Fe3 plus. And it'll do this in conjunction with oxygen molecules, and in the process generate reactive oxygen species. A reactive oxygen species is something that has an unpaired electron in its outer orbital. Chemical reactions are basically transfer of electrons. That's the main thing that's happening with chemical reactions. And then when you have an oxygen molecule with an unpaired electron in its outer orbital, it wants all paired electrons. It wants an octet, 8 electrons really in its orbital typically. So the point is, it'll become extremely reactive, like a hydroxyl radical, for example. And then having a hydroxyl radical in the body is like having a super ball and you bounce it around, it just starts bouncing around, breaking things. That is the danger of these reactive oxygens. They can damage DNA, cause mutations, lead to increased cancer risk. They can damage proteins, make proteins dysfunctional. And this can become autocatalytic, where it just continues on, generating numerous reactive oxygen species out of proportion to the amount of free iron. So you really want to have next to as little as possible free iron in your body. Okay, so how do you minimize that? Well, the more your body becomes overloaded with iron, the more predisposed you are to having free iron get into the blood or into the cytoplasm of a cell. In addition, if you have something causing cellular tissue death, like let's say you're an alcoholic and you're damaging liver cells, or you eat too much industrialized fructose, sweetened drinks of any type like soda pop, you'll have liver cells that die. The liver cells store tons of iron. So they're especially bad. When they die, they can release a significant amount of iron into the blood. Okay. The reactive oxygen, as we spoke about, it can cause cell death when it happens in a cytoplasm, called apoptosis. Special type of cell death called ferroptosis, ferro for the iron, and it's really from lipid peroxidation. It can cause lipid peroxidation in other locations, including on the intermitochondrial membrane. We spoke about that before, and it can cause lipid peroxidation in the cardiolipins, which are PUFAs, polyunsaturated fatty acids, and so that really will destroy mitochondrial function. You want your mitochondria to work well. That's where your energy comes from. Okay, where do we get iron from? We get iron from eating meat because of the heme iron. You don't have hemoglobin in general in plants, so you get tons more iron from eating meat. Iron cookware is a bad idea. There was a population in Africa called the Bantus, and they used to have all this iron cookware. They had really high iron levels. You can get it from some of these vitamins. If you ever see a vitamin with iron in it, don't take it, okay? You don't want to become overloaded. Some persons who work with mining iron, they can inhale it. Why is iron, again, such a big deal? Because it increases your risk of infection or cancer. Everybody, by the way, has a bunch of dormant bacteria inside their body. Bacteria go through your mouth, they go through your gut, and they get tiny amounts into your blood. And those bacteria typically can't grow because they don't have any iron. They need iron to grow, to reproduce their proteins and their enzymes. So what happens is a lot of these bacteria can go into dormancy. And when people first hear about dormant bacteria, they go, oh, really? Is that true? Think about it, okay? Tuberculosis will stay dormant in our body for decades. All right, syphilis, stay dormant in our body for decades. Lyme disease, Borrelia burgdorferi, it'll stay dormant for decades. Herpes type 1, herpes type 2. In addition, there are other bacteria and viruses that can be dormant in our body for prolonged amounts of time. Bacteria are kind of tricky, all the things they can do. They can live sometimes inside of red blood cells. They can live sometimes inside of white blood cells as a way to shelter themselves from the immune system. So there's more dormant bacteria than one would realize in our blood, and when free iron becomes available, they can sometimes become reactivated. And that's one of the dangers sometimes of blood transfusion is reactivation of dormant bacteria. In addition, cancer cells need iron to grow. They need a lot of it to grow rapidly. So one of the ways that the body protects itself from an infection, of course, or cancer is by sequestering iron as much as possible, keeping it away from any infectious or cancer cells. What is normal iron levels in the body? Normal is a serum ferritin of 25 to 75 nanograms per milliliter. Now, we talked about ferritin. It's for intracellular storage. It really should not even be in the blood at all. But everybody has a few cells that are dying here and there, and they'll release a little bit of ferritin into the blood. And when it's released into the blood, it'll not uncommonly leak some of its 4,500 iron atoms, and so you'll have a little bit of free iron. Women are protected up until menopause by their monthly menstruation. It's equivalent of a therapeutic phlebotomy, so they tend to have much lower serum ferritins than the equivalent age man. But women start accumulating iron after menopause. And men, like I said, start accumulating it after 20 years of age. If you have excess free iron, you also have increased risk for Alzheimer's disease and Parkinson's disease. So you can see this is pretty bad. Increased risk of infection, increased risk of cancer, increased risk of myocardial infarction, increased risk of Alzheimer's disease, Parkinson's disease. And the more iron deposition a person has in their brain, the more likely they are to be demented. So what else can it do? Reactivation of dormant bacteria. Sometimes the gram-negative rods will release something called LPS. That's for lipopolysaccharide. And the gram-positive bacteria can also release something similar. It's called LTA, lipoteichoic acid. Okay, but either way, they can cause deformity of the fibrinogen in the blood, making it more hypercoagulable. And it can cause a hypercoagulable phase in the blood and predispose them to thrombotic events. In addition, this hypercoagulable process can lead to a change in the structure of certain proteins in the brain. Normal, let's say, beta amyloid protein is what is called an alpha helix, meaning that it's cylindrical. You can look through it, let's say. And you can change it. Same sequence of amino acids, but it can change the beta pleated sheet. And those can form hydrogen connections from one to another and stack up like a bunch of them together, a big aggregate beta amyloid. And it's thought that alpha-synuclein, the protein associated with Parkinson's disease, can do the same thing. So what am I talking about? This mechanism of dormant bacteria reactivation with subsequent release of LPS and LTA leading to a change in the fibrinogen, making it more hypercoagulable, leading to a distortion of these extracellular proteins, can cause them to precipitate. A protein has to be soluble to be functional. So when they become insoluble, the beta amyloid or the alpha-synuclein with Parkinson's, and potentially the mechanism with tau I'm less certain of, but what I'm saying is, how is it that a protein can function like a prion and self-propagate? Because it'll have something like this to initiate the process. So anyways, what can you do if you're iron overloaded? And you probably are, by the way. If you're a guy and you're over 40 years of age, What do I think is a smart thing to do? Donate blood. You got to talk to your doctor, make sure you don't have any, conflicting other medical problems, but you want to try to keep your serum ferritin below 75 to just lower your risk of these problems, because a lot of times the reason people are sick and kind of going down the tubes is not just one easy to isolate problem, it's multiple problems. So what you want to do is try to optimize everything as much as you can. So donating blood, you have to, do it with your physician's supervision, but you have to space it out long enough and then recheck your hemoglobin afterwards, make sure you don't become anemic. But it can take a lot of donations. Like let's say your serum ferritin is 400, which is a common in guys who eat a lot of meat. It'll take you many blood donations to get it down to where you want it, but at least you can get the process started. So that's our coverage of iron overload, and the big thing that causes the problem is redox cycling of free iron with the generation of reactive oxygens and free radicals like hydroxyl radical being produced, and that ends up going through what's called the Ferritin reaction and the Haber-Weiss reaction. So this is actually a big subject. This is just an introduction to it. We can talk about this more in the future, but this is a good thing to know, and there's an easy solution. Donate blood. Also exercise a lot and sweat off the iron that you can, but you can only sweat off so much iron. If you break a sweat every day, you're making progress. Think about all the stuff you see on your t-shirt, it's not just pure water coming out of you when you sweat. So anyways, hope that's helpful.